So if we want to run a hypothesis test on a standard deviation or a variance, we're going to do a chi-square test. So let's remember the chi-square distribution. So it's a right-skewed graph. The total area is 1. All of our chi-square values are positive. And it works under the degrees of freedom. And for us, degrees of freedom will be n-1. So our hypotheses, remember how the table works. I'm sorry. So the table that we have, the table that I'm going to use, I'll show you a picture. It has a little key down here at the bottom. So right here's the chi-square graph, and it's telling me that the area, the alpha that I see, has to be the area to the right of the chi-square value that I see. Okay. So if I'm going to do a left tail test, in order to get a chi-square value over here on the left, I have to give the entire area that's to the right of that chi-square left value. Okay. I'll try to do an example. Okay, so the alpha in our table has to be to the right, and I'll go ahead and put that in quotes. So we'll have to be careful on one tail left and two tail tests. We can still do them, we just have to be careful. Okay, so what are the hypotheses going to be? So, right, the null hypothesis still has the equal, the alternative hypothesis still has a greater than, or right, one of the others. The others could be right, less than or not equal to. Okay. And then some number, and these two numbers have to be the same. So I've written this one here for variance, right, sigma squared for variance. Exact same idea if they are standard deviations, right? We just have a sigma in both places. So critical values from the chi-square distribution, degrees of freedom, already talked about it, alpha value, look under, draw the curve, and use the alternative hypothesis to determine those critical values. Now the test value formula. This looks really different than test value formulas we found before. So it's n-1 times s squared, so that's the variance from our sample, divided by sigma squared, the variance from the hypotheses. So the s squared from the sample and the sigma squared from the hypotheses. Okay, so let's go ahead and do an example. The average movie admission price for a recent year was $7.18. The population variance was $3.81. Oh no, it's variance, so it's not actually linear, is it? Because it's squared. A random sample of, okay, so here it sounds like we're getting some info. I'm going to go ahead and start writing that. A random sample of 15 had a mean of, I don't think I need the mean, right? Because if I look in my formula, there's no mu's or x bars or anything there. So I think that's just extra information I have to look past. Had a mean of $8.02 and a standard deviation, so this is from our sample, of 208, and alpha is 0.05. Is there sufficient evidence to conclude the variance is different? Okay, so now I'm ready to write my hypotheses. I got a little clue there. So first off, it's on variances, so I'm going to use sigma squared. Same in both. The null always has an equal sign, right? And we're comparing it to the population variance, right, that someone told us before. And so now we're trying to see, is it different? Is this new information different than 381? Okay, and there's nothing like screaming out that the null hypothesis is our claim. So in that case, we almost always go with the alternative hypothesis. Okay, so what else do we need to do then? I guess we need to draw our curve and find our critical values. So let's do that. I'll sneak mine over here. So alpha is 0.05 and it's a two-tailed test. Remember, the not equal says two-tailed test. That means I need to share that alpha. That 0.05 gets shared. So I'm going to have 95% in the middle, right? Alpha of 0.05, that's 5%. So 95% in the middle, which means I have 5% to share in each tail. So this tail over here will be 2.5%, as will this one, 2.5%. But now remember how the table works. So to get that chi-square right, I'm going to look up 0.025. Oh, I guess I need my degrees of freedom. So my degrees of freedom will be 14. So let's go ahead and put the table up. So again, alpha is the area on the right. So if I just look at my picture, the area on the right is going to be 0.025. So I'm going to find my 0.025, and I'm going to come down to 14. So that is a blue line on mine. So 26.119. Now for the chi-square left value, that area, the area to the right of that line is the 95 in the middle plus the 2.5 over there on the right. So the area I want to look up to get this chi-square value is 0.9725. So the 95% plus the 2.5% gets me that 97.25. I know it's getting kind of crowded in there. Sorry about that. So here's my 0.975. Why did I write 25? 0.975. I was thinking I should write that or show you the addition. 0.95 plus 0.025 is 0.975. Keep myself honest here. So coming down the 0.975 column to the 14 row gives me that chi-square left value of 5.629. Okay, so I'm going to go ahead and circle these two numbers, right? Those are my boundaries. So if I go either less than the 5.629 or more than the 26.119, then I can say that it's different. Okay, oh my gosh, let's find our test value. So the test value, there's your formula, so n minus 1 times s squared, so s from our sample, so 2.08 squared, divided by sigma squared from the hypotheses. So calculator, and what do we have then? 14 times 2.08 squared divided by 3.81 squared gives me a test value of 4.17. So that is smaller than my left critical value. So I am in the left rejection region. That means we get to say that it's different. So our decision, we're going to reject the null hypothesis. We're in the tails. We're in the rejection region. So then our summary, there is enough evidence. So we're rejecting the null, so we get to support our claim. And I don't have room to write more about the actual movie prices, but if I did, I would. Okay, so let's do our next example. And it looks like I've got some data here, so we'll go ahead and input that. I'm going to get my calculator ready. So I get it ready by going to the Stat menu and Edit, and I'm going to clear out a list. So I arrow up to the top, and I hit Clear, and then I hit Enter, right? And that wipes out the whole thing. So I'll show you on the L2. So arrow up till it's highlighted, and then the clear button, the clear button's over here kind of by the arrows, and then enter down at the bottom, and that'll wipe out a list. Okay, so I have that ready, so let's go ahead and read our question. A machine fills 12-ounce soda bottles, or bottles with soda. For the machine to function properly, the standard deviation of the population must be less than 0.03 ounces. A random sample of 8 bottles is selected. Okay, info, that sounds like M equals 8. And the number of ounces of soda in each bottle was given. Oh, okay, well, that's all I've got then. Alpha is 0.05. Can we conclude the machine is functioning properly? Okay, well, let's circle back through and let's find those hypotheses. So it's about standard deviation, so sigmas, and it's an equal in the null because that's what we do. The standard deviation must be of the population, so that's this guy, must be less than 0.03. So they told us the alternative. So the null is just equals 0.03 because the numbers have to match. So I have a one tail left. And I could find my critical value. So see, I think I've got a little bit more room over here. Let's go ahead and sneak that graph in here. So it's alpha's 0.05 and it's on the left. So I need the chi-square value that cuts off the left 0.05. So again, because that's how my table works, if I want 0.05 to be on the left, that means I have to look up 0.95. So n was 8, so our degrees of freedom are 7. So I'm going to come down the 0.95 column to the 7 row. So that value is 2.167. So the tail is my rejection region. If my test value is less than 0.2167, then we're going to reject. If it's greater than, then we go into the fail to reject business. But I don't have any data. I need to put all of that, I need to put my list of values into my list. So let's go ahead and do that. So 12.03, and then enter 12.1, enter 12.02, enter 11.98, 12. Trailing zeros, right, we don't need to include, and in fact, the calculator might actually take them off if you try to include them. 11.99. Okay, I'm going to look them over just to make sure. Okay, awesome. And then it's stat, calc, and we want the one variable statistics, right? We want the standard deviation for this sample. And I don't have a frequency, it's just, right, the data that we had. And there we go. And it gives us a whole bunch of stuff when we don't need all of it. We just need that, right? And it's from a sample, so we'll take the SX. So 0.0426, where am I going to round that? I'm going to start writing. So for my sample, the standard deviation is 0.04268. I guess that's where I'll stop. Okay, so let's go ahead and find our test value. So the test value is n-1, 7. Standard deviation from our sample, so 0.04268 squared divided by standard deviation from the hypotheses. So I'll quit this mode. So second quit takes you out. And then here we go, 7 times 0.04268 squared divided by 0.03 squared. Enter. So that test value is 14.168. So where does that live on my chi-square distribution? Well, it's greater than 2.16. So my test value is over in the do not reject region. So that's what decision I'll make. So my decision will be not to reject the null hypothesis. And then our summary, our conclusion, there is not enough evidence. Oh, I didn't say what my claim was, so let's think about that. Can we conclude the machine is functioning properly? So it's functioning properly if it's less than, so I'll go ahead and make that be my claim. Do not reject the null. There is not enough evidence to do not reject the, so we can't support the claim that we'll just say the standard deviation is less than 0.03.